This is a recording for you to get you started with linear regression. And I'm going to go through some of the basics here of linear regression, and then I'm going to give some pictures that will show kind of a graphical interpretation of what you're looking at and what you're trying to determine. And it's important to be able to relate back to that picture, because what you're going to see going forward is a lot of the software is going to automate this for you and give you some results. But if you don't have something to relate that back to, then it's not going to be very meaningful. So keep these pictures in mind as I go through here, and we'll talk about those. Here's a little overview outline of what you can do with linear regression. You generally start with scatter diagrams, and then you look to see if you've got a positive association, a negative association, and that's displayed in terms of what you would have as a slope coefficient if you put a line through those data points. There's an occasion where you might say that there's no association, where it looks kind of like maybe you fired a shotgun, and that's what the scatter diagram looks like, and you don't see, well, there's no pattern in that data, so there's no association there, and my model should reflect that. And the fourth instance there is an example that I'll show you here in just a moment, but it was an example of very, very bad data collection because it had very limited predictive range. Second thing that you want to do is you're going to try to come up with what's called the line of best fit. And we haven't said what that means, but we'll talk about it here in a little bit. Third thing, you're going to look at what's called an analysis of variance table for linear regression. And from that, you're going to determine if there is a statistically significant linear relationship between two variables. And you're going to do that by way of an F-test for significance, and you could also do it as a T-test for significance. And some of the software will show you both, and for simple linear regression, they are exactly equivalent tests. So you'll have that information. Fourth situation there's other applications that you can get into with linear regression. You can introduce dummy variables. There's a great area of application called analysis of covariance, and I don't believe we cover that in any of the courses here, but it's a great application for linear regression. And if some of you are interested in that, I can put together a little example to show you how that works. Then you can take it from there and go on to multiple regression and nonlinear regression, all sorts of other areas of application, and we're going to show you lots of those. All right, here's where you start with a scatter diagram, and you're looking to come up with a way to make predictions about y using some information about that predictor variable, capital X, down there across the horizontal axis. The basics of linear regression, you're coming up with a linear equation for predicting values in some variable y. To do that, you want to have a simultaneous collection of measurements on X and on Y so that you can come up with a meaningful relationship there. Now, keep in mind that topic that you're doing here doesn't say that X causes Y. It just simply means that there's an association between those. For example, if you look at weight to predict height, it's not going to help for you to gain weight thinking that you're going to get taller. That just doesn't work, and it doesn't make sense. All right, here's the cases that I'm going to talk about. We're looking for a line of best fit, and the first example or picture I'm going to show is one where there's a positive association, a positive slope. Second one is a negative association. Third example will be no association, and then that fourth one will be one of very limited range. The line of best fit, still in quotes, because we haven't said what it means yet. Okay, start off, and you could take these, and when you work through this and look at the data, it'd be a good exercise for you to try to draw a scatter diagram of your own with the pairs of points I'm going to give you in just a moment, and then eyeball that scatter diagram and try to decide how would you estimate the slope and the intercept for the line that would go through there. And it looks like a familiar formula for the equation of a line that you probably have seen before. And just by eyeballing, you should be able to determine what you think the line of best fit is by superimposing that on your scatter diagram. Okay, here's the 4 data sets, A, B, C, D across the top, and then I got X sub I, Y sub I's by each of those, and they give some very different pictures. And here's the first example, and the X sub I, Y sub I's are plotted there. And if you were to eyeball a line of best fit through there, you would probably start with it where you would put B0 somewhere, maybe about 6 point something. And for the slope coefficient, maybe a -1 would probably give you a pretty good fit through that data. Next example for that data, if you were to eyeball this one, you would probably put a slope coefficient again, approximately 1. And for the intercept, probably somewhere down around 0. So you think, well, that's probably a pretty good fit for that line there. The third example, this is the one that more or less reflects what it would look like if you chose to fire a shotgun with a piece of paper. You just got a random assortment of points there. And probably the best that you could do for this one is to say, well, you know, I think my slope should be equal to 0, and my intercept should be equal to 5. Well, that's probably a pretty good determination to say that the slope for this instance here is equal to 0, because in fact, that's what we're going to test when we do a hypothesis test later on. And I'll refer you back to this picture, and you'll say, well, I'm going to test the hypothesis that the slope coefficient is equal to 0. Well, that's equivalent to saying, looks to me like a shotgun was fired with that piece of paper. So that example is one that you want to keep a mental picture of that and keep referring back to it, because when you get to what the software puts out, it's just going to give you a bunch of numbers, and you're going to have to be able to interpret that in terms of something that's meaningful to you, and hopefully you retain this picture throughout here. Next picture, look at this. You're trying to make predictions about Y based on values for X. Well, you don't have any data outside of this very limited range right here. So, you know, in looking at this, you would say, well, that's not even appropriate to try to come up with a linear model there. The data collection for this was very poor, and it should have spanned a much bigger range there. So 4 different cases. One's a positive slope, one's a negative slope, one is a slope that looks kind of like equal to 0, and the 4th example is one where it's very poor data collection. All right, now we're going to introduce some formulas and talk about all this by way of an example. This one's a good example for linear regression. It's one, I think it's fairly popular in some textbooks. You're looking at age blocks in years, and you're seeing an increase there in blood pressure versus age. And it looks like you ought to be able to come up with a pretty good linear relationship going through pretty close to those data points there. Yeah, let me give a little bit of theory here. I've got my simultaneous measurements there, age, blood pressure, pairs of observations. I want to come up with an equation for the line which best fits that data. And the model I'm going to use for that is my y hat, my predicted values, will be equal to some intercept, B0, plus a slope coefficient, B1, plus some error. And it might be error in measurement or some other source for error, but we'll talk about that error in just a moment. But we want to make sure that what we do is we come up with a model that makes that error in there as small as possible. All right. Here's kind of an introduction to what that's going to look like. I put some points there on the axis, the vertical and horizontal axis, and I've got a formula up there at the top. The y sub i's in that formula represent the little red dots on there. Actually, they're little red squares. The y sub I hat would represent the predicted values from my model. So if you look at this formulation over here, I'm trying to measure the difference between what my model would predict, y sub I hat, and then the true value, y sub I. So in terms of my picture, if you go to 2, I got my little red block here. That formula up there measures the distance between this little red block here and to that line. And then it takes that difference between those two values and squares it and adds them up for all of those points. So it's simultaneously, so I want you to add all of those up, the predictions versus the actuals for that particular line that's been drawn through there. That's what we call the E sub i's, the errors for this model. And it's the E sub i's squared, added up, and we call that the sum of squares for error for this particular model representation. So this is a kind of a nice visual picture to have in mind for what you're doing with linear regression. You're looking at that sum of squares for error, and you're going to try to come up with a line through there that makes that number as small as possible. And so you might think, that probably doesn't look very good. Maybe that line should have been shifted down a little bit right about to here. And so you can think about that, how you might draw it, but what you really want to do is come up with a formula that's going to give you the best possible line through there, and that's what we're going to do. The way you do that is you find values for the intercept and for the slope that minimize that sum squared for error. And the way you do that is you take partial derivatives for the SSE with respect to each of those variables. You set those equations equal to 0, and you solve. And if we work through that, it would probably take probably close to an hour of hard writing to come up with these solutions here. And if you want to find those solutions, there's a lot of textbooks out there that'll show you how to do that. And by the time you get through with it, you're probably going to be very bored and waste. Why don't I just use the formula? Anyway, the solutions for those are called the least squares estimates for the intercept and slope. They're also known as ordinary least squares estimates. And the line through there is called the line of best fit, also called the regression line. Why do I give you all those names? Because people use them all. And so you need to just be familiar with that so that you know when people are talking about this, what they're talking about. So if you work through with the data, you would say, well, in order to solve this, I can't just do the first one up there. I have to have B1 first. So I drive down to B1 and say, okay, I'm going to take my data points and I'm going to sum the products of the x sub I, y sub I. So multiply them together, add them up. Then I'm going to take the mean for the x's, the mean for the y's. N is the number of data points that I have. Then I'm going to calculate over here in a formula the x sub I values, the x values squared, add them up. I'm going to subtract from that the number of data points again, and then the mean for the x's squared. So I can put this into a spreadsheet and make it pretty easy to calculate. But then once I've got that, I go up here and put my B1 in, my Y mean, my X mean, and I got the B0 there too. So pretty easy to calculate this by way of a spreadsheet. And here's kind of automating that calculation for that blood pressure data. I got my age groups there, 35, 45, 50, and so it's really nicely spread out there. And then the mean blood pressure, the Y sub I is 114, 124, and on down. And then at the bottom, I've got the sums for each of those, and then the bottom line across there is the mean. So the mean age is 55, the mean blood pressure is 141, and then calculating those things that I needed for my formula, I did the x sub I, y sub I. So it's 35 times 114 should give me 3990. X sub I squared is 35 squared. That should be that number. So I calculate all of those down there and then put the sums across the bottom. So those are all of the things that I need in order to do, with a hand calculator or with a spreadsheet, to go back and figure out what the values for B0 and B1 should be there. Okay, there's another picture of it with my scatter diagram. And I just left these in there as copies and pastes from Excel. So if you wanted to go back and use Excel to play around with this, you can. Anyway, plugging back into my formulas then, my B1, using the formulas that I calculated there in the spreadsheet, plugging all those numbers in, I get 1.38 for my slope. Put that in the 1.38 with the means here, and my intercept is 65.1. So my line of best fit would be y equals 65.1 plus 1.38 times x. So that gives me everything I need right there then to determine that line of best fit. But I still haven't done anything to test it to see if it's really significant. And so here's just a little instruction there. If you want to play around with this in Excel, you can double click on the data for blood pressure, copy paste it into Excel, make your own scatter plot. You can select chart from the toolbar, select add trend line, and you'll be able to produce that chart that's shown next. So you can get your values for age, blood pressure. There's your line of best fit through there. Each of the data points is replicated so you can see the picture there. All right, now we've got to do a little calculation here to figure out how do we go about determining if this model is really significant or not, or should that B1 value just be used as equal to 0, and then we would just use the mean for the y sub I. So we start with a mathematical identity there. Y sub I minus y sub I hat, that's the predicted value. And we add and subtract the mean up there on the right-hand side. We square both sides, sum from 1 to n. And if you want to go through the mathematical gyrations on that, what you get when you simplify that down is it looks like this. You get the y sub i's minus the mean squared. Well, that's what's called the total sum of squares. The total variability of the y values about their mean is represented by this quantity right over here. And then it's abbreviated as SST. Sum of squares total means what is all of the variability measured about y bar, the mean of the y's. On the right side over here, it's the y sub I minus the y hats. Remember, that's the error value. So if I take those error values here and square them and add them up, that's the sum of squares for error. That number should be really, really small if my model is a good one. Last part of that, now I have the predicted values again, the y sub I hat minus the mean. Well, that's the sum of squares due to my regression model. How does this look over here in comparison to this quantity back over here if this one's really small? So my sum of squares for regression should be really close to the sum of squares total, and the sum of squares for error should be really, really small if I have a good model here. All right, how do we go about measuring that? Well, here it is kind of explained again. My sum of squares regression divided by sum of squares total should be close to 1, and that's that quantity you've probably heard of called R squared. All right. This is that information now summarized in what's called an analysis of variance table. And there's some interesting things that go on here. That total sum of squares is down here across the bottom. That's the formula for that. The error sum of squares is in this little block here. And then the top one, it's sum of squares for regression. Now these are additive. So if I know sum of squares total and I know sum of squares for error, I can get this one by subtraction. I take sum of squares total minus sum of squares error should give me this number right up here. Now, a little more information here. There's a column for what's called degrees of freedom. And the total degrees of freedom is always the number of pairs of points that I have. N is the number of pairs of points minus 1. And my degrees of freedom for regression is 1. And so these are also additive. So n minus 1 is equal to 1 plus n minus 2. So that's what goes here. Now there's some more information that goes in here, and this is what's called a mean square. And a mean square is sum of squares divided by degrees of freedom. So my mean square for regression is equal to sum of squares for regression divided by 1, so it's just sum of squares for regression. My mean square for error is equal to the sum of squares for error, SSE, divided by degrees of freedom, which is n minus 2. Now these are important quantities because we're going to use them again here in just a moment. And I really should have brackets on this n minus 2 because you're dividing by the whole quantity there, n minus 2. So insert that for me because I forgot it there. So carry that on. We're going to keep this, coming back to this. This is a picture that many software products will print this out for you, but you need to understand what's going on there and be able to relate it back in terms of quantities that you understand. So let's keep going here. Now, the big question is my model really any good? Is there a statistically significant linear relationship here? And the way you're going to answer that is you're going to take your analysis of variance table and the R-squared value, and you're going to answer these questions about blood pressure. You're going to summarize that data, an analysis of variance table, and then you're going to do a couple of hypothesis tests here, and I'll show you the output from Python and also from Excel. But the question comes down to, what do you think your hypothesis test is going to look like? Well, you need to relate it back to those pictures that I did back in the beginning and think in terms of that one picture where it looked kind of like a shotgun, and the slope coefficient for that was equal to 0. So you're saying, I think maybe if my model is no good, then it should look like that. So what I want to do is I want to test the hypothesis here that my slope is equal to 0, because I think I'm going to reject this hypothesis. Otherwise, I wouldn't have been doing all this work. The other way of stating it is to say I'm going to test a hypothesis that my slope coefficient here, B1, is equal to 0, thinking back to that picture I have. Another way of stating it is to say, well, it's not statistically significant, but they all mean the same thing. All three of those statements mean exactly the same thing. Now, my alternative would be that that slope coefficient is not equal to 0, and that's what I want to be able to conclude. Otherwise, I wouldn't be going to all this work and putting all these numbers together just to end up with something that was not statistically significant. Now, how am I going to make that determination? Well, I'm going to make it in terms of a probability distribution. And here's those calculations that I replicated here. I got my sum of squares for error, my sum of squares total. So I ran through those calculations so I could populate my ANOVA. Total sum of squares, 1936. Sum of squares error is 31.6. I don't need to do the sum of squares for regression because it's found by 1936 minus 31.6. So let me jump on a little bit further here. And there it is displayed now. In terms of that analysis of variance table, there's my 1936, 31.6. I have 5 data points, so I've got n minus 1 here is 4. N minus 2 is 3. My sum of squares error, found by subtraction, with 1 degree of freedom, is there. And so my mean squares then are 1904.4 divided by 1, 31.6 divided by 3 comes out to 10.5. And this is the information I need now to be able to look at in terms of a probability distribution, because the ratio of 2 mean squares, this number divided by this one, follows what's called an F distribution. So we're going to go compare it to that. And think about it in terms of an F distribution. If this number is really big, I'm going to get a result that's way out in the tail end of that probability distribution. And that means I'm going to reject the hypothesis that my slope coefficient is equal to 0. So I'm looking at these numbers right now. I'm thinking, wow, this number here divided by 10.5, that's going to be really big. I already know that I'm going to reject that hypothesis, and this model is going to turn out to be statistically significant because I've already seen how big these numbers are by comparison right here. So jump to the next one. There's my F ratio. It's the mean square regression divided by mean square error with their appropriate degrees of freedom. So it gives me an F value with 1 and n minus 2 degrees of freedom. And when B1 is significantly different from 0, that ratio is going to be a big number too. Now, I can go to Excel and plug in some numbers and see what this turns out to be. It should exceed the F value from Excel. If I type in equals F inverse 0.05 degrees of freedom for numerator, degrees of freedom of the denominator, then as long as my model is bigger than that number, I know it's statistically significant. But I'm going to put it in terms of another way. I want to do it in terms of a p-value. Here's another way to do that. My number there turns out to be that ratio, F ratio is 181.4. And with 1 and 3 degrees of freedom, I can go to Excel and say, well, how significant is that in terms of p-values? Well, it means F dist F, comma, numerator degrees of freedom, comma, denominator degrees of freedom. So I put in there 181.4, comma, 1, comma, 3, and Excel gives me a value of 0.000885. And what that represents is the probability of getting a value greater than 181.4 from that F distribution based on chance alone is less than 0.001. And so that means this model is very significant in terms of that p-value. Now, if you don't know some of these things and what p-values are and so forth, you might want to do a little going back and studying that so that you understand the things I've said here. If you're still confused by some of the terminology I'm using, send me some questions and I'll try to give you some more detailed answers about what you can do to read about F distributions and p-values and some of those things that you can focus on to get a better feel for what's taking place here. Okay, so the answer to all of these questions was, is this model really good? The answer is yes. Is there a statistically significant linear relationship? Absolutely yes. How significant is it? It gives a p-value that's less than 0.001. And many times your software will just report it this way. It'll calculate that p-value, and it won't give you the exact number like I looked at there. It'll just say p less than 0.001. That's why I cut it off there, because that's generally what software does for you. Now, here's the Python code that I did for this, and then the output for it, where it gives a summary of the results. And it gives the R-squared value there, 0.984. It also gives the coefficients for those models. For age, the coefficient 1.38, the intercept 65.1. Now, the equivalent test of what we did there is in terms of a t-distribution here, and it calculates a t-value of 13.446. Well, the p-value associated with that is going to be less than 0.001. So we're getting the same sort of information here that we did from the other ANOVA, but just presented in a slightly different way. Now, there's a lot of other things that are in here that you're going to find out more about later on. It also gives the F-stat there, too. Log likelihood, AIC, and BIC, we'll talk about those later on. But for right now, just feel comfortable with, oh yeah, I know where most of these numbers are coming from. When Python gives me this output, it's a model that's ordinary least squares. The method is least squares. It minimizes that sum of squares for error, and all of these things that you kind of know how they're calculated in there. So you'll have a comfort level when you see that. Here's what it looks like if you do the output in Excel. It gives you the R-squared value up, and these are going to be slightly different in the different software products. Excel gives you the analysis of variance table. It gives you those sums of squares, mean squares, the F ratio, 1904 divided by 10.5, and it gives you the significance of that over here, 0.000, or, less than 0.001. And here's those coefficients in here also. It also gives you those t-statistics, so you've got another way of looking at that test with a t-stat or with an F ratio. So two different ways to kind of compare the test results that you're getting there. Now here's some other properties of linear regression that you might find useful in the future. The sum of the residuals is always going to be equal to 0. The sum of the squared residuals, as you know, because of what we talked about, is going to be the lowest it could possibly be when you have this model, because that's what it guarantees. The sum of your y sub i's will always equal the sum of the predicted values. And your regression line will always go through x bar, y bar, the mean for the x's and the mean for the y's there. All right, just a couple more. Just a warning here, watch out when you're doing regression for an extreme value. Something like that can really influence the regression coefficients that you come up with. So you have to deal, we'll go through some methods for dealing with things like that. Here's a little practice data if you want to go through it and kind of replicate these calculations in Excel and make sure you feel like, yeah, I know how those all come together now, and I can reconstruct that analysis of variance table, and I know how to make that test then to see if it's statistically significant. So that's it. That's where I'm going to end, and I hope you enjoy this and find it useful to get your understanding. Going forward, you're going to see a lot of computer printouts, but you need to be able to relate it back to something in terms of a picture. So hope this is helpful to you. Stop recording right